All right, so welcome to lesson for geodetic surveying or geodetic computations dated 22nd of March to 2022. And we're continuing on with our geodetic theory and computations. And so by way of revision, we've gone back to our notes and back to our ellipsoid, which was our starting point. And we used an ellipsoid to fit the shape, to approximate the shape of the Earth, but to create a series of coordinates or a coordinate system that can be used for position anywhere on the Earth's surface. It had certain parameters that defined its size, shape, and its position. It was geocentric, which meant the centre was placed, mathematically at least, to the centre of mass of the Earth. And the centre of mass of the Earth would be defined by gravity measurements all around the Earth's surface. The coordinate systems that were based on this ellipsoid, there are two. One is geographic coordinates, the other one is Cartesian coordinates. The geographic coordinates are made up of latitude, longitude, and ellipsoidal height. They're three-dimensional. The Cartesian coordinates are made up of X, Y, and Z. Again, they're Earth-centered coordinates. So any position on the Earth's surface can be described in latitude, longitude, and ellipsoidal height, or in Cartesian coordinates in X, Y, and Z. Having identified our 3D world-based coordinate system, we sought to convert that into a way that we could lay out our coordinate system on a flat piece of paper. Because maps over time have been on a single piece of paper you can lay out on a desk and look at. The first attempts created distortions in the maps, and there was various alternate ways of doing it until finally they decided on, finally decided on the transverse Mercator projection, transverse meaning sideways across, and it's similar to a cylinder. It's fitted to the ellipsoid and then rolled out. It only touches the ellipsoid in one place, and that's one of the meridians of longitude, and then it's rolled out. So this was the transverse Mercator projection. It's actually, in a way, like physically, that's fine, you can roll that out, but behind the scenes, a lot of mathematics that convert those ellipsoidal coordinates into flat coordinates. And that process is called projection. And our projected coordinates are grid coordinates on a flat 2D map. The transverse Mercator projection was further amended to remove distortion, and it was amended to the universal transverse Mercator projection. And that's what we have today. And that projection creates the zones across the Earth that's used by all countries. And in Australia, so there's 6-degree zones, there's 60 degrees, and we, apart from the zones, each zone, the centre of each zone is fixed at a meridian of longitude, and each zone is also have a false origin to ensure that the grid coordinates in each zone are not negative in the southern hemisphere. There's various parameters that pull that together that define that. The longitude of the initial central meridian, which is zone 1, 177 degrees west longitude. So that meridian, that prime meridian, is actually halfway around the zones. Zone width 6 degrees, central scale factor 396, false easting and false northing are written there in the diagram. This UTM system is has been used with this GRS80 ellipsoid, GRS geodetic reference system 80 ellipsoid and GDA 2020 latitudes and longitudes to define the map grid of Australia 2020. And we looked at the zones, how they affect Australia, and then how they affect New South Wales. And most of our work will be in New South Wales. We looked at a bit of a blow up of our zone 56. Central meridian is 153 degrees longitude. The true origin of coordinates in our grid system is the intersection of that meridian of longitude and the equator. But in the southern hemisphere, that would cause negative coordinates. And so for all zones across Australia, we have a false origin, and that gives us positive coordinates anywhere in that zone. And these parameters, if you like, are replicated for every zone. So every zone has a false origin. Every zone has a central meridian, which is a particular meridian of longitude. And so it's important that we always aware when we're working in grid coordinates, we're aware of the zone, because we could have the same coordinates but in a different zone. So always be very careful of that. So last week we watched a little video just on the reasons why we're moving from GDA 94 to GDA 2020. Mainly it was because of plate tectonics, the movement of the Australian plate over time. And then we looked at coordinate transformations. And this was the process of changing coordinates from one reference frame or datum to another. And it's done by a similarity transformation. And we looked at GDA 94 to GDA 2020. And we downloaded a transformation conversion Excel file, and we use that to do a little calculation as part of exercise 1. And in the end, we try to get a feel for the error on the Earth's surface for some of the differences that are apparent between using the Excel spreadsheet to calculate GDA 2020 and comparing that to the GDA 2020 values from Skims Online. And I made a note down here that's important, that the transformation spreadsheet uses a conformal projection that does not include the distortion. So there was a note in our notes here, and I'll just find it. And that is, it is recommended that in New South Wales, it is recommended that the transformation model that is used is both conformal and distortion. And the one that we downloaded for the purposes of our exercise was only conformal. Didn't include the corrections for distortions, and that's why we had some slight differences. Okay. So this week we're going to introduce coordinate conversions. And this is the conversion of coordinates from one coordinate system to a different coordinate system. So Cartesian to geodetic, to geographic, geographic to grid. So before the transformations were from geographic in one datum to geographic in another datum. So and they were called transformations. Coordinate conversions are when we convert from a different coordinate or a coordinate system to a different coordinate system. So MGA 2020 is a grid system, and GDA 2020 is a geographic system. So different sorts of systems, and we've got some formulas coming up that we're going to use to convert coordinates, and so we see how they're being used. Okay, so this conversion is modelled mathematically by Ruger-N series equations and Kruger-Lander series equations, also called Redfern's formula. And there's two formulas, two spreadsheets, and they're used in different circumstances. So if we're in the same zone, and typically mostly we are, our survey's in the same zone, it's a pretty big area, we would use this Redfern's formula, so the Lander series. So the Kruger-Lander series equations, also called Redfern's formula, are used for conversions from and to geographic and grid coordinates within the same zone. Yep, and we can download that, and I've asked you to go to this website and download that. Well, just before we do, we'll have a look at the other one because we want to download the other one as well. If we're doing calculations across multiple zones, it's hard to imagine why we would, perhaps for some scientific reasons. We want to do calculations across Australia. We would use the Kruger-N series equations and for multiple zones. So you can download both, but we're going to use the Lander series Excel file for a series of calculations. So I'll give you a couple of minutes just to go to the Moodle and or go to this website and download those two spreadsheets. I've actually downloaded them and put them on the Moodle for you. So whichever's easiest. So I'll just give you a few minutes to do that.
Ian, there's a few. Is it the Kruger-Lambda series or N series?
Both.
So those are the two? Cool.
That's what I said.
Sorry, yeah, no, I just wasn't sure which two it was because there's just multiple on the website.
So again, this is the Lander series, and I've just done a screenshot from what you see if you click into the geographic to grid, And so they've got Alice Springs there as a sample. Similar to the transformation spreadsheet we're using, where the user input is grade and the result is in blue. So in this case, it's a matter of entering values in the grey and then clicking over to the grid and having that grid values defined for us. So, geographic to grid. So the grid values are there. If we want to go from grid back to geographic, we use the other one. Yep. Okay. Now we've got some data coming up to use in that. But before we do, I just want to define a couple of variables that we see here. It's got grid convergence and it's got point scale. Grid convergence is the angular quantity to be added algebraically to an azimuth to obtain a grid bearing. In the southern hemisphere, grid convergence is positive for points east of the central meridian and negative for points west. Now, where is grid north? Grid north is on the grid, it's just vertically up. When we're on the MGA, so Map Grid of Australia grid north is parallel to all the other vertical lines. The grid convergence is the difference between true north and grid north. Yeah? True north and grid north. So true north is from the point on the ellipsoid up along a meridian to the North Pole. And so down on the grid, there's a slight angular difference. If we project that true north direction, there's a slight angular difference between that true north direction and grid north. And the difference is the grid convergence. It varies on depending on which side of the central meridian you are, because on the right-hand side, the meridians are curving from the bottom out and then back in. And on the left side of the central meridian, they're curving from the South Pole out and then back in towards the top. And so that's why it's positive to the east and negative to the west. In some weeks' time, we'll actually get right into the calculation of a traverse on the grid. And there's a whole lot of calculations involved in that. And we're just sort of heading our way there, if you like. Point scale. The ratio of an infinitesimal distance. So the zeros are very, very small. At a point on the grid, to a corresponding distance on the ellipsoid. It's a value, it's a very small value. You just got to understand what it is. That it does come up from time to time, and we see it. We'll see it in various calculations further down the track. Okay, so I've actually got some data for you. You've got this now. Once you put it in and come up with some values for easting and northing for Bega and Scone, and then use the same spreadsheet, but in the opposite context, come from grid eastings and northings back to latitude and longitude. And where do you think we might check our values? Let's just put a note in there. I'll give you a few minutes to do that. So we're just getting used to doing some calculations. Helps us understand the coordinate systems, the different coordinate systems, how to move between them. Now I'm going to write in red what I get, and I want you to just confirm it, whether Do you think it's right or wrong? So Brandon, I've sent Cameron a link.
No worries, Ian. I think he got in, actually. I think he did.
Yeah, all sorted.
My bad. I should have updated you.
That's all right. He's always challenged having problems with his electronics, I think. Okay, so maybe it's Charlie's put some coordinates in there. He's just copied off mine, of course. No, we'll
I got the first one right. The second one I have.
bit of a different. Yeah, so we need some confirmation from somebody else on the screen. I might have written it down wrong.
I know this sounds so silly, Ian, but I've completely forgotten to put a decimal place, and it's completely given me the wrong answer. I apologize.
I need to apologise. Just have a go again.
Yeah, I'm getting what you're getting.
Where would we go to check our values? Thanks, Alex.
I can't remember the website off the top of my head, but there's a website to be able to check where Scone's point is. I'll have a quick Google.
Is it not just Skims?
Perfect schemes, 6 maps.
There was a it wasn't off Skims. I'm pretty sure there was a. Oh, we got to order it. That's correct. Yeah, sorry, my bad.
You got to order nothing. Don't got order nothing. We'll soon find out.
CauseNet?
Yeah, isn't there a station list on CoreSnet?
That's where we went last time. So CoreSnet is the place to go, provides some really great information, coordinates, latitude, longitude, all sorts of things about all our CoreSnet stations. Different from SCIMS. Why do we use CoreSnet? When do we use CoreSnet? Come on, you guys part-timers.
When we're looking for stations? Or is this, and I'm assuming that what we're doing now is just an arbitrary coordinate.
When we're doing GPS work?
So, Ryan, what'd you say?
When we're doing GPS work.
Yep, and how do you use CoreSnet?
You link in, like when you turn on your controller, you log into it.
Yep.
And you need login details and stuff.
You do, and your firm pays a license fee to gain access to the knowledge. You know, why is it good, or what are we using it for in terms of GNSS?
Because it's updated. Is it real time, or it's
Well, it's very good.
always
for sure.
updating?
You pay for it to eliminate the error in GPS.
We'll talk about it in a sec. Talk about it in a second. Just put these in. Well, Wesley. Yeah, well, it's used in mining, but I'll talk about it in a sec. Let me get these. Anyone done Kumi yet?
Just doing the second one now.
Yeah, my answer should be in chat.
Oh, you didn't both. Yep. So I got this information from CoreSnet, really high quality data. The stations, if you like, measuring their location really all the time. Now, why do we use CoreSnet stations in GNSS? Well, it saves us from having 2 units in the field. To get real-time position with GNSS, you need a rover and you need a base station. Those 2 units, this is how it used to be before CORS. Everyone bought 2, you had to take 2 out the field. So one was set up, the base station set up over some fixed mark, and the rover could then move around. The idea being that the base and the rover are picking up the signals from the same satellites. They're in slightly different positions, and so the dual measurement they can resolve the errors for position. The base station talks to the rover, talks to it via typically a radio link, and it's sending corrections to the rover so you can get real-time position at the rover. And that's how it always was. You had to buy 2 till they came up with CoreSnet, because surveyors aren't the only ones that use satellite positioning, of course. It's used extensively, agriculture, mining, everywhere. And this is pretty accurate, so car navigation is plus or minus 5-10 metres. But if you want any accurate from that, you need these two, so a rover and a base station. And so we have a series of base stations called CORSNet that are broadcasting their position all the time. And so, yes, you've got to go to get the information. You go online and go to their website and actually download the base station corrections. Yeah.
And just quickly on that, say if you're out rural and you set up your base on a PM that doesn't have good coordinates, like it's not, it hasn't been fixed properly, what do you let your base run for a long time, and then those coordinates are going to be different to what your PM's reading?
All sorts of things there. So out in the country, I've blown up the little map, and you notice out in the country, out in really the Western Division, there's a lack of marks and there's some gaps between the core stations. But most of Western New South Wales is covered pretty well. Most rural surveyors would also have a antenna to be able to pick up the signal for longer distances. But typically in the country, the big issue with CORSNet is phone coverage. Phone coverage. So the further you get away from phone towers out there, if you lose your telephone signal, you can't use cores. So even though it's New South Wales generally pretty covered, there's big gaps that probably still apply, certainly out right near the west. And for that, you'd probably have to go back to a base station and a rover, and the base station set up over a known point. Yep. So PM, SSM, good quality, and then to broadcast a longer distance. So rural areas, where you want to be connecting to your rover over a couple of Ks, they set up an antenna. So to boost the radio signal over a longer distance. Does that answer your question, Ryan?
Yeah, kind of. It's pretty good.
So we looked at, so we've used this Kruger Lander series, and we've done a few calculations. So remember, this is used for calculating within one zone, and so we can't use calculations that go across zones. So this is the second one, and this is same data, and I thought we might just replicate it. Yeah, replicate it and see if we get any difference. Compare the results of the two spreadsheets. What are the size of the differences? Yep, so use the second one and plug it in and see what we get. I think it'll be probably pretty close, but let's see.
Yeah, I think I've screwed up in my understanding of this table and like changed things that didn't need to be changed without like understanding how this table actually works.
So that's all right. Just so you're only entering the grey area. So the blue is sort of calculated for you, yeah? So in either...
Yeah, I just saw that there was a field for the central meridian, and I saw that we had a given zone.
Yep.
So I changed the central meridian to that zone. It doesn't seem like I should have.
Oh, I'll just change it back.
Yeah.
So we do have the central meridian for the zones, because if we look at our notes here, that's why I pan back up the top. There we go. Central meridian for zone 55 is 147. Central meridian for zone 56 is 153 degrees.
So it being set to 135, are you not
What?
able to change? So on the projection on the actual grid, it's set to 135.
Well, that's grade, so it says user input.
Yeah, I think that's why he changed it, and that's why probably all getting different results. Although I'm getting the same result as what I assume everyone else would be getting if had you not changed it from 135.
Oh, I think you've got to change it, don't you? Makes sense.
All right, time to do the last question all over again, everyone.
So, bigger. So I'm doing it off to one side here. And I'm getting pretty well the correct results. I'm getting easting, northern correct, zone correct. So I imagine, even though it's recommended only to be used when you're using multiple, so use this in a combination with other calculations, but I imagine it's fine if you're just picking up 1 point, so it seems to work okay. So I'm getting, for mine, where is it? Brain stopping. Oh, here we go. So, so I put in Vega, latitude, longitude, and I get that. Yep. I'll just check one of the grid to geographic. Try that. Okay, so what's everyone getting? All right.
Which question are you asking us for?
Richard, so you posted some coordinates. Which ones are they for, friend?
That was good question.
So you posted two, could have been the previous ones. No.
No, that's bigger and Scone.
I believe it's the second lot of Bega and Scone.
Yeah, I got the same.
So Richard,
Yeah.
I'll just whack in. So I assume these are what you're giving me. I want everyone to check these. They don't compare really well to the other ones.
So that's what we're getting also, but that begs the question, do we bother changing the central meridian longitude now that the zone are different?
Hang on, one step at a time, mate. So Richard, these are yours for Bega, is that right?
That's right. Yeah.
Okay, so let's go and find it, and I'll share it with you. Central meridian for Bega is um, so I'm getting a little bit different there. And that sort of agrees. So easting and northing for Bega, we come up to here, and that's, so they're pretty close. 025, 521, 522, zone 55.
Yeah, I see. I didn't change the central meridian.
Yeah, user input is the grey stuff.
Yeah. Gotcha. Got me.
Okay, so got a few more guys putting in stuff. Yep. Tribby looks like he's pretty close. Wesley, is that for the next one or something? So Scone, let's have a look at Scone. And Scone's 56. Central meridian 153 degrees. And 132. 298868, 2988686111, 645 1888002. Yep, zone 56. Now let's check. So they check out all right. So it shows you that if we just stay within the zone for this, even though this is made up for multiple observations across zones, it still gives us the right result. So let's try the grid to geographic. So this is Glen Innes and Cooma. So user input. So these are fixed for us, semi-major, flattening, central meridian. So, sorry, these are user input, the grey stuff, but we're not going to fiddle around with anything bar the central meridian, the name, and of course the coordinates. Notice they don't have the zone. They don't need the zone because they have the central meridian. Yep. All right, so we want Glen Innes. Yeah. And so that should have calculated for us. And there's our, this is from CauseNet, minus 29, 44, 36.7575, 75752. Slight difference. Longitude, 151, 06, 003, 68. It's pretty good. And we'll check Cooma as well. Cooma zone 55. See where I got the central meridian from? Remember in our notes we had that little diagram of New South Wales. There's the 3 zones that cover New South Wales. So that's where I got them from. So this is Cooma, and Cooma has these coordinates. And we finish up then with minus 36, 14, 073, 1106. So 0311, 07 to 06. And then latitude, longitude 149, 07, 38.01519. Spot on, really. So it works, either one works for what we're using them for. Okay, well done. Okay. Any questions?
I'm a little confused as to why Sam and Sarah have gotten a 155 as their degrees when you have gotten a different answer, unless they've gone ahead and they're answering something different, and that would make more sense. Right, that's probably what's happened.
Well, I'm confused too.
Sorry, they've just put in a chat a different answer for Cooma, and I'm just trying to work out why, that's all. Sorry,
so,
you know, they're using the other spreadsheet, so they've just gone a little ahead. Sorry, my apologies.
Yeah, I think I, again, in my updated version, once again, forgot to adjust central meridian.
So central meridian, user inputs, all the grey stuff. We don't bother about, let's not fiddle around
Yeah,
with
just
those.
changes it to 149, yeah.
Yep. Did it work?
Probably. Yep, that fixes it.
Okay, so that's cleared that up. Okay, so we're going to move on. Okay, so calculations so far have been number one, transformations. Transformations from, let's just go back. Go back. Coordinate transformations. Yep. Coordinate transformations. Process of change coordinates from one reference frame or datum to another. Yep. GDA 94 to GDA 2020. Yep. One reference frame to another datum. Transformations. GDA 94, GDA 2020, or reverse. Now we have conversions, coordinate conversions. Converting a conversion of coordinates from one coordinate system to a different one, but in the same datum. Same datum, yeah. Geographic to grid. Yeah, this is geographic, GDA 2020 are geographic coordinates, latitude, longitude, etc. To grid, map grid of Australia, or the reverse. Yeah. Two ways of doing it, well, two types of calculations, and we have this Kruger-Lander series which is adopted for calculations within the one zone. Yep, within the one zone. So we just did a little exercise where we actually used both on the same set of data. We got the same results, which is great. Okay, so transformations, coordinate conversions. Okay, so that's number two in terms of the mathematics that we've sort of dealt with. So I'm going to come on to the next one. Coordinate computations. Coordinate computations. This will take a few weeks to get it, set it down and get it right. So let's not rush it. A little bit to understand. Coordinate computations. So number one, reduction of measured distances to the ellipsoid. Due to the effects of atmospheric refraction, light waves or microwaves used by EDM, electronic distance measurement, follow a curved path. Before this curved path distance can be used for geodetic computations, it should be reduced to the surface of the ellipsoid by the application of both physical and geometric corrections. Now, our EDM, does anyone know what type of light is used by our EDM, our modern day ones?
Infrared and visible.
Yep. So generally for pointing, a laser pointer, infrared, you can see the dot. Sorry, visible. Infrared is generally the one, that's right. So it's a light wave at a certain frequency in the infrared frequency, and they use that. The early ones...
I believe it's a set of frequencies so that it can take measurements on multiples of 10 to get the decimal places and things.
Yep. On the early days of distance measurement, they used, where are we? So actually they did use microwaves.
They started with microwaves, yeah.
So anyway, so because it's electromagnetic radiation that's passing through the atmosphere, temperature and pressure, if you like, model the atmosphere. And because that varies along the path, we get refraction of that wave. So it's in a sense, it's bent. So we have to take into account that. It's actually a curved path. The distance measures on a curved path. That's the diagram you see in every geodetic textbook about distances. And so here we are, we're at A and B, and let's just not pretend there's no instrument heights here. We just pretend we're on the ground. We're at A, we're shooting a distance to B or measuring a distance to B. And so our wave path distance T1 is that curved distance. The straight line connection between the two is the slope distance. So we have little d1, little d2. So one's the arc, one's the straight line, is the chord. The straight line connection is the chord. We then have this level terrain distance. It's a bit odd, but it's between the mean height of the stations A and B, their mean height. You understand as we work through it. And then we have another line. Oh, okay. So B is at this level. Yep. And then we have the geoid. So we have the geoid, this wavy line running through there is the geoid. We have sea level, geoid sea level. That's the wavy line. This curved line is the sea level distance. So they're modelling it A and then at B, and then it's comes up with an arc. It just produces an arc because it doesn't take into account the changes between the two. And then we bring it down further. Here's our grey, here's our brown. That's our ellipsoid. That's our ellipsoid that we started with on day one. So our mathematical model that is the reference frame for our coordinates, our 3D coordinate system for the Earth's surface. So down here we have then the curved distance, which is the ellipsoid distance, and the straight line joined between the two is known as the ellipsoid chord distance. Okay, heights. When we observe our height in latitude, longitude, we get an ellipsoidal height. Ellipsoidal height is shown as little h. Little h. There's little h A standing for station A, little h B standing for station B. It's the height of the point above the ellipsoid. Yep. Height of the point above the ellipsoid. Now it's pretty useless in reality for us. We need something that approximates Australian height datum. So the geoid is used. The geoid models mean sea level through the ground, across the ground. It's modelled. It's modelled using gravity measurements and various points within Australia. The difference between the ellipsoid and geoid is modelled by a separation value, and that separation value is big N little a standing for separation at point A, and big N little b for the separation at point B. They're different because the geoid is like a big sort of wave. It's not a nice smooth surface because the gravity changes. So, and then we have capital H, so big H equals that's the orthometric height, and generally that's the bit that approximates AHD. So it's the ellipsoid minus the separation gives us something that equates to AHD, and that's big H. Okay. It's pretty complicated. It's a bit hard to get your head around that, but we'll keep working on it. So due to the effects of atmospheric refraction, for us it's going to be infrared. Infrared light used by modern day EDM follows a curved path. before this curved path distance, red is where we've measured the distance, before it can be used for any geodetic computations, it's got to be reduced from there all the way down to an ellipsoidal distance S. Yep. It's got to be reduced from the red arc progressively in steps down to the ellipsoidal distance. This is a diagram straight out of your reference document. So, how is it done? There are two types of corrections. One's physical and one's geometric. And I've just added a little bit of information about the physical corrections, but in fact, we can ignore them. Yep. The difference between D1 and D2 is very, very small. Is very small for distances up to 15 kilometres. Yep. Accordingly, it can be ignored. The corrections are, we have an atmospheric correction, and I've just written a little bit about the first velocity one because it relates to what we do with our theodolite and our parts per million correction. So first velocity correction is when we measure temperature and pressure in the field, and typically theodolites, modern day theodolites have sensors to sense that, and they update the parts per million. But go back a few years, you would take a pressure gauge and a temperature, a thermometer, measure those, and then plug those values into the theodolite to update the parts per million. Parts per million would affect any distance that was measured by that value. Yep. And so it's like a scale factor.
That's what we have to note that down when we do the baseline surveys.
Yeah.
Plug that in.
Yeah, good on you. Yep. Yeah, so typically you set your parts per million to 0 on the baseline, and you measure temperature and pressure, and you do those corrections separately. That's what we always learn. I don't know whether you did that right.
Yeah, so we enter them into a template after when we get back to the office.
Yes, but the theodolite in the field that you use
Set to 0.
Set parts per million to 0. Yep.
Yep.
Okay, so this is just a little explanation of that one. Yep, and not going to talk about those, don't really need to know because they're so small, we can ignore them. So the other sort of corrections are the geometric corrections, and these must be applied to all measured distance. We have a slope correction, an ellipsoidal correction, and an arced chord correction. So the slope, now remember that in reality, D1 is the same as D2. So the notes refer to a wave path chord distance. So this is the wave path distance, but it puts a little word in there saying chord to represent the straight line connection between our 2 points. So let's come back and have a look at that. So D1 equals D2. D2 is the wave path chord distance. So the slope correction reduces that to a horizontal distance at mean elevation of the terminals of line A and B. This corrected distance is called the level terrain distance. So where is that? Here it is here. So this level terrain distance is this flat distance between A and B, this flat distance. So it reduces the chord down to that. Now somebody many years ago sat down and worked all this stuff out. We don't have to worry about how they're derived. We just try and understand the process so we can apply it to a survey. So the slope correction is the correction from our wave path chord down to the level terrain distance. Yep. The ellipsoidal correction is the level, is a correction that reduces the level terrain distance down to the ellipsoidal chord distance. Let's have a look at that. So from this level terrain distance, this next correction brings it down to the ellipsoidal chord distance. So the straight line connection, but it's the chord distance. It's not on the ellipsoid. It's the chord that connects the 2 points that sit on the ellipsoid. The production of those. And then finally, the arc to chord. So arc to chord. Here's the arc to chord. So chord to arc, in fact. What they call that, arc to chord. It reduces the ellipsoidal chord distance to the ellipsoidal distance. And this is what we're trying to get at. Little s. We're trying to start up at the wave distance, the measured distance, and we want to reduce that to an ellipsoidal distance, which is denoted by little s. Yep. How are we going to do that? The notes take you through either this combined formula or the separate formulas for each. Sorry, I lose my voice. Each correction. Yep. We're going to use the combined one. And I've just taken an extract so I don't get the formula wrong. So this is from page 46 of your reference document. There's two formulas. One calculates D3 and the other one uses D3 to calculate the ellipsoidal distance. So one converts the wave path distance or the wave path chord distance down to the ellipsoidal chord, and then the next formula gives us the ellipsoidal distance, which should be a longer distance. H, so the little h, remember, that's the ellipsoidal heights. We have this other constant or variable, well, sorry, it's either one or the other. It's actually constant for us. It's the radius with alpha as a subscript. And it's the radius of curvature in the azimuth of the line. In the azimuth of the line. For distance of 30 kilometres in the Australian region, the arc to chord correction is 28 mils for 30 kilometres. So it's pretty small. For a distance of 50, it comes up to about 0.13. The second term of the arc to chord is less than a mil for lines up to 100. So you notice in this second formula, there's no term, there's no second formula term, it's got a plus, ... It's been dropped out because it doesn't mean anything in terms of the final result. So again, let's have a look at, so ellipsoidal height, little h, that's the distance, sorry, that's the height of the point above the ellipsoid. That's what we get out of our raw height, out of our GNSS controller. Orthometric height is the height of the point above the geoid measured along the plumb line. So that's big H. Yep. Height above geoid, which is approximating the height of the point on AHD. Yep. On AHD. Because this is approximating AHD through the ground. Through the ground. Remember, in real life, and we go out in the field, we would always measure, if we're using GNSS, we always must measure or connect to survey control marks, SCIMS marks, because they give us the best connection to Australian height data. Yep. So GNSS gives us an approximate HD when it uses the geoid, but not as accurate as using the SCIMS marks. Good enough for some purposes. So I've added the HD height here. So, and then we have the ellipsoid to geoid separation. There's a little formula that relates those three together. So the height on Australian height datum equals the ellipsoidal height, which is the big one, minus the separation. And that gives us something equating to AHD. You notice I've written the subscript AHD for N well, typically it's an approximation, and therefore our height, our orthometric height, is also an approximation of AHD. Radius of curvature of a point at a given azimuth. Azimuth is defined by the relationship to true north. True north is 0 degrees on the ellipsoid. Yep. Goes on to say for most solutions, the mean radius, geometric mean radius, can be used instead of the radius of curvature, and I'll put in a number for that for our ellipsoid. Yep. Okay. This would be page. So just bear with me. Okay, we started out, so these are measured distances, converting measured distances. So we set up, we're measuring, you're not measuring 50 meters here, we're measuring a very, very long way, because only at that point we have to make these corrections. We do another unit in second semester, which is conduct geodetic surveying. And then we actually go out and we try and replicate the distances for geodetic surveying that actually allows to create to have some corrections, because mostly we're so limited in being able to make observations. So we used to go up to a couple of different trig stations, do some observations, try and use those. In previous years, we went to the University of New South Wales, got on top of their observation deck on the surveying building. We could see about a couple of Ks to Sydney Harbour Bridge. There's a light there with a coordinate and various other ones on the horizon. And from that, we can actually, there is some corrections we can apply. All right. So now we start up here. These are coordinate computations. Before we can do that, we have to reduce our measured distance to the ellipsoid. Yep. Measured distances. Now, what about measured directions? There are our angles, yeah, our directions. Sorry. Measured directions. Okay. Our reduced direction is derived from various corrections. We have our observed direction. We start with what was measured in the field. We then have to make a correction for deflection, skew normal correction, and then this Laplace correction. These are all very small. So let's have a look at this first one. So this is what we measure. So this is an angle. Angles now, angles, not distances, angles. Directions are like bearings. Yep. Deflection correction. Deflection correction relates to the deflection of the vertical. And I've dragged this out of the reference. It's a little bit hard to see. But you can find it on page 55, maybe a little bit clearer. Now we're talking about really small amounts that have no effect on 99% of surveys that we do. Really small amounts, but as soon as we measure very long distances, it does have an effect. And so it's taken into account. So deflection of the vertical relates to, so we have a point we're observing on the Earth's surface. if we push a line from there that is perpendicular to the surface of the ellipsoid, and then produce that all the way down to the equatorial plane, that line is the normal to the ellipsoid, or the prime vertical. But in actual fact, when you set up your theodolite, you put a, just imagine, you put a plumb line on it, plumb bob. It actually points to the local centre of mass in that area, and not actually down along that prime vertical. Yeah. So the normal to the 90 degrees to the ellipsoid runs through it. The point we set over and runs through the telescope all the way up does not actually go down and hit that point. It actually is square to the ellipsoid. That makes sense, doesn't it? If the plumb line is direction of gravity, and the geoid in that area is also defined by gravity, then the line that comes up from the geoid comes up square to the geoid at that point and passes through our observation point. That's actually called the plumb line. And there's a very, very slight difference between the two. And that's called the deflection of the vertical. The deflection can be in two directions, in a north-south and east-west direction. It's a bit complicated. So this is all, somebody sat down and to resolve this mathematically so it works in all cases for all distances, we have to take all this stuff into account. So this is why it's here. Okay. Again, I've just taken an extract out of the notes to define some of these points. The main one I was after, because we've talked about the ellipsoid, ellipsoidal height geoid, the main one I was really after is the deflection of the vertical. Deviation of actual gravity, gravity observed by the gravimeter from normal gravity, approximation of actual gravity used using a model ellipsoid, is made up of two components, north-south component, deflection in the prime meridian and the east-west component direction, prime vertical. Right. So I don't want to make it too complicated, but it's just the difference between this normal line which comes down, hits the ellipsoid at 90 degrees. If we go back into our notes, all the way back, all the way back, all the way back. And to this little diagram that I've got on page 5 of your notes, you notice our point P there, we've got a line from P that comes down through the meridian, yep, sort of below it, directly below it. And then that line continues on, passes through the equatorial plane to hit the vertical axis. And this is how latitude's observed. But it comes down and hits the ellipsoid at 90 degrees. And because it's an ellipsoid and not a circle, not a sphere, it doesn't hit the center of the reference frame. It goes either a bit below or a bit above. It'd be very close, but it doesn't hit it perfectly. But anyway, that line intersects the ellipsoid at 90 degrees. Yep. So at that point, though, we have local gravity, which is points which, if we drop that down, it's a different location. And so that's the deflection. Yeah, so we push those two up. One's going up that way and one's going slightly to the side of it. Hope you can understand. A little bit hard to grasp. I couldn't find a really good diagram. And so, blah, 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 and it's made up of two components, one a north-south, because remember, it's pointing up, but part of that's going like deflecting from the normal line, slightly north-south and slightly east-west, if that makes sense. Hopefully it does. Okay, I can show you on the whiteboard about it. Okay. Yep. And then finally, so that was that first one. We've got the skew normal one and the Laplace correction. Let's have a quick look at those. I've just included some definitions for those. For two trig stations spaced apart, the normals to the ellipsoid, so that's from each point, that line going down, that's 90 degrees to the ellipsoid. For two different points, those two lines aren't parallel. And so because of that, there's a small correction to be made, but it's very small. And finally, this Laplace correction corrects the difference between astronomical and geodetic azimuth. Okay, so when we talk about geodetic azimuth, that's in terms of true north. Astronomical azimuth is actually observed in relation to the stars. And I imagine, don't know a lot about it, but it's in relation to the stars, and I guess the definition. Sorry, I'm going to confuse myself. I'm going to confuse you. I'll try and explain it, but we're just going to leave it like that. It's based on the stars, like azimuth from the stars. We used to, when I was at university, we were able to determine latitude and longitude by observing certain stars. And so I imagine I related it back to that, saying, okay, if we can determine position on the ground from observations of stars either in the southern sky or in the eastern sky or the western sky, we determine latitude and longitude, then that, having done that, we should be able to define zero, and that would be not true north, but some sort of astronomical north. So there you go. Okay, and we're going to finish up today with a little exercise. A little exercise where you sit down and create a worksheet that reflects those two equations. And I've got some input there to test it out, see if it works for you. So the two equations I'm talking about are these two. Yep, that one and that one. So the R alpha is constant. I'm giving you that value. The little h and the little ha, little hb are the ellipsoidal heights of the 2 points. And that's about it. A few little calculations in Excel. You're all experts at Excel now. And so once you've got D3, you then have to use D3 in the second formula to get little s. We're trying to get little s. Yep. And I've given the answer down there. I'm hoping that's correct. I'll pick that up. So we'll see. I use the formula for S and somebody made a note. You got an answer 830 mils off. Who was that? Sam. So you're able to plug that in okay?
Yeah, seems all right. I don't know if it's exactly right since I haven't looked at done a full check of exactly what I've put in, but I don't think I would have made a big mistake.
Well, let's see what everyone else says.
Yeah. It's pretty simple.
There you go. got to do, sorry, I lose my voice, just got to do something. So everyone work on that and we'll see whether we get some confirmation of the result.
Just gonna quickly leave the class and rejoin because I'm having issues with my Teams.
Ty, you got two answers there. Okay, it's about 10 past. We're not going to proceed any further past this point tonight. So for everyone else, please come back and just put that in. Make sure you get the formulas correct, and we'll have a look at the results next week. So I've got 99.85. So it's get a bit of variety between different answers. Wesley, can't read yours. 0.9. 94.9. We need a couple more decimal places, Wesley. So we're going to finish up there. As I said, please finish that little calc and see how we go next week. And we'll push along then with our more calculations, because in actual fact, this is what this is all about.
Sorry, before you were to go, Ian, I just want to confirm I've just been a little bit struggling on the second formula. So once we get past, we add in all the formulations and stuff, the plus ... I've forgotten what that is, because I've just gotten the wrong answer for the first one. I've got to redo it all. Sorry.
The plus ... is nothing.
Okay.
So the plus ...
beautiful.
used to be a term, but it's not used because the correction it calculates to is so small, it's negligible.
Okay, cool. Just making sure. Thank you so much.
So thanks everyone. We'll catch up next week, and we'll catch up
I'll see you tomorrow night.
in PSP. We'll
Thank you.
continue on with our depositor plans and stuff. So thanks everyone. Have a good evening and a good week working.
Cool. Thanks,
All right.
Ian.
Thanks, Ian.
Thank you.
Thanks, Ian.
Thanks, Ian.